Hello, everyone, and welcome to the 58th Cambridge Cheminformatics meeting. We will start. First of all, with some housekeeping messages. So please, for everyone here in the building, use the tablet at the entrance to register your name, sign in, and sign off when you leave. We don't expect any fire alarm at this moment. We have them on Wednesdays at noon. So if there is an alarm now, it's a real one, and then slowly keep going down the building by the normal exits, and then we meet in the fire points. And please follow the instructions from the fire evacuation officers and get ready in the assembly point in the car park. First of all, some announcements. So the CCDC is hiring. So, maybe I need some. Hello?
It's fine. The audio is fine.
For now.
Yeah. Is it better now? Can you hear me?
Yeah, it's fine. Yeah, online is fine.
In the room. Do you have the microphones in the room? So. Okay. How about now? Is the same? Okay. Hello. I need to lean on the microphone. Anyway, I was saying, continue with the announcements. So the CCDC is hiring. We have 4 positions: junior software engineer here in Cambridge and hybrid, administrator, data coordinator, Cambridge, UK, hybrid and remote, product portfolio manager, Cambridge, UK and hybrid, and finance business partner in Cambridge, UK. For more information, please refer to our webpage to get more information about these 4 positions. And another good news is that we are celebrating this year the 60th anniversary of the CCDC, and we plan to run some events, so please keep on posted, check our webpage to see what we're organizing. And then on behalf of Kemal Kopruloglu, there is announcements about the Comp Chem Tools hands-on workshop for graduates in career in the area. So this year is being held in Leeds at the studio on Tuesday, 8th of April. Registration is following this link. The slides will be available, so please go and check them. And the students will be able to try different softwares in the area of computational chemistry from different providers: Medchemica, OpenEye, CDD Bolt, CCDC, Schrödinger, and Pharmacelera. So there is an early bird registration program with some discount, and looking forward to meeting you there. And then continuing with the meeting, we aim to bring together different people and scientists in the area of cheminformatics, extended area of cheminformatics, including structure-based drug design, ligand-based drug design, cheminformatics, AI, machine learning, together scientifically. And personally, this is a meeting for everyone to enjoy and meet new people, more scientists, more colleagues, and enjoy in person and also in a hybrid mode. So the format is 3 talks of about 10 minutes, followed by a question and answer session. And at the end of the 3 talks will be a session for some drinks in the near pub in the Panton Arms. So we have prepared already the calendar or the agenda for the year. So the meetings will be, this is the first one, 19th of February. The next one will be on the 23rd of April. The third one will be on the 3rd of September, and the final one on the 12th of November. All the agendas will be published, and more information can be found in the webpage www.c-inf.net. Thanks to the RSC, Richard Seal, and Emily Clark at the CCDC for sponsoring and organizing food, and to the CCDC. For us, I'm reading this on behalf of Andreas Bender. And the main meeting will be recorded, so the information and the slides will be available whenever the speakers allow us to have the slides. So the question can be posted on the chat window, and we will read them at the end of the presentation to the presenters. After the last talk, please stay online. There will be a session, virtual session for people to chat with the rest of the online attendees, and the people in the office here. We can go to have some drinks in the Panton Arms. If you wish to present next time, please contact Andreas Bender for an slot in the next meeting. And without more dilation, the three talks today will be these ones. So we start with the first speaker, which is Morgan Thomas. So Morgan Thomas conducted his PhD with Professor Andreas Bender here at the University of Cambridge, where he predominantly worked on generative AI for drug design in collaboration with Nexera Pharmaceuticals. After graduating, he moved to Barcelona in direct response to a quarter-life crisis, after he said, where he continues to work on generative AI with Professor Gianni De Fabritis at University Pompeu Fabra, in collaboration with Johnson & Johnson. There he discovered that despite the relentless sunshine and Mediterranean lifestyle, he remains passionate about computational methods and advanced drug discovery. So his talk is identifying novel nanomolar A2A receptor ligands by combining docking and reinforcement learning. So now the floor is yours. If I share the screen.
Thanks very much, Kepa. I hope it says that I cannot share because it's disabled. Here we go. Let's see if this works.
20 minutes of...
How's that?
Yeah, we can see it. Is it on purpose?
Sorry, what on purpose? Is it full screen?
Yeah, but it looks like two images that are a bit distorted or a bit shifted.
Reference, something like
that.
Yes.
Yeah, that looks better.
Perfect. Yes, exactly. Thank you.
I think there's a delay. I think that's the problem. How about now? Can you see it yet?
It's loading. Still loading.
Always a good start.
Well, it's normal, right?
Okay, I'm going to go out of full screen and go back into full screen again.
Yeah, that we can see now. Yeah.
So, okay.
I think that works. You can keep it like this. It's big enough.
Can I keep it like this? It's still plenty visible.
Yeah.
Okay, perfect. I'll keep it like this then. Okay, yeah. Thanks very much for having me and inviting me. It's quite strange to be here remotely as opposed to in the room where I usually am. But today I'd like to talk about the identification of some novel nanomolar A2A receptor ligands by using generative methods combined with docking and reinforcement learning. So I think quite a lot of people are quite familiar with what's called chemical language models now. But just for a quick recap, this work involves the use of chemical language models. So what are chemical language models? Well, in this example I'm showing, you have effectively what are a sequential autoregressive model. So here I have the example of gated recurrent units, but this could apply also to other models, such as more popularly transformers now, where you have effectively sequence by sequence, token by token generation autoregressively. So in this example, you might have a training instance, which is paracetamol represented in its smile string notation. And you simply pass to the model the go token, and it will predict the next token in the sequence. And it will pass a hidden state from one time step to the next time step. And you effectively train your model to correctly predict the next token in the string sequence. What this means is at inference time, you can effectively pass in your starting token, such as your go token.
We can see this.
I should have gone to the next slide.
Yeah, no. Still not. Slides are trying to come, but it's not successful yet.
Okay. Yeah. It seemed to have stopped sharing, but I should be sharing again now.
Yeah. No, still, we don't see anything.
Okay, let me try one more time.
Yeah, maybe share your, no, you share your full screen, right? Or maybe share only the window or bury something in that setup.
Yeah, let's try that. I'm trying just the window now instead of the entire screen.
Still, we can't see anything. There is a message reading that you started screen sharing. Double click to enter full screen mode, but we don't see anything yet.
Okay, one last. How about now?
Still the same. Yeah, not much advanced.
Okay. The only thing I can think to do is to close my web browser and open it up again.
Okay, let's try to do that. Otherwise, maybe we can, if you don't mind, you can send me the slides if you're okay with that.
Yeah.
We move to the next speaker, and then we share the screen from here, and then you can. Well, try with the restarting your web browser, and if this doesn't work, we move to the next speaker, and we try to sort out the things in the meanwhile.
Okay.
Yeah, now we can see the screen.
Now you can see the screen.
Yes.
It seems incredibly delayed.
Yeah, but the other screen, the email we've seen, not the PowerPoint or whatever.
But you don't see my Google Slides.
No, it's there.
Okay. Very strange. And if I go into full screen mode, can you see that?
No, is it loading? No.
Okay, let's ignore full screen mode.
That's fine. Now we see the slides.
Okay, let's ignore full screen mode. Okay. So moving on quickly.
Okay, thank you.
Yes, so at inference time, it's just a matter of inputting a first start token. It will predict the next token in the sequence, which you sample from. So it will predict a probability distribution over possible next tokens. You simply sample from that probability distribution, sampling your next token in the string, and you iteratively or recurrently feed that back into your model until you sample a completely de novo smile string. So in this case, where the training instance might be paracetamol, you might sample a molecule that looks very similar, but not quite the same. And actually, it's been shown for quite some time now that these chemical language models are very capable. So they're very capable of generating almost 100% validity in terms of the smile strings, close to 100% uniqueness, as in not sampling the same molecule over again, and almost 100% novelty with respect to the training data. So actually sampling completely de novo molecules. Moreover, the property distributions learned by the models closely represent the property distributions of the training data set. So you're also operating in a similar property space. And what's quite nice is actually it's been shown that you can expand chemical spaces by up to approximately 1,000-fold. So this is a particular study where they trained, I think, on GDB13, something like 0.1% of the data set. And then by sampling, they can recover something like 70% of the data set. And actually, if you account for molecules that are very close to the data set, then it's more like 1,000-fold enrichment in terms of the chemical space you can access. Now, what you really want to do is you want to optimize the chemical properties of de novo molecules. And with chemical language models, you can think of really two main approaches to do this, let's say. So on the left-hand side, you have fine-tuning. So you have a particular data set, a much smaller data set of molecules with already similar properties as those that you want to generate. So for example, this could be molecules active against a certain protein target. And you simply do a couple of extra rounds of training on that smaller data set, and you fine tune your model towards that area of chemical space. So then you generate molecules that are similar to your project data, but of course you don't always have project data to fine tune your model on. And in practice, what you see is sometimes a lack of kind of significant novelty or sufficient novelty with respect to, practical things like whether you're in a new patentable space or not. And actually, these models have been quite extensively validated now. So what I mean by that is there's been quite a few publications where they've actually experimentally synthesized some of the molecules and tested them to see if they're hits against certain targets, for example. On the other hand, you can use an optimization approach such as reinforcement learning, where you take your model and you iteratively sample de novo molecules from that model and you score them with scoring functions, or in other words, an oracle, and return scores back to your model and update your model in such a way that you generate molecules to try and maximize those scores. So you don't necessarily require project data, depending on what scoring functions you have. But there come other difficulties with this, such as you might end up exploiting your oracle if there are particular limitations with the scoring functions you're using, and multi-parameter optimization can be particularly difficult. Now, to combine these for structure-based drug design with tools such as docking, there comes an extra problem, and that is the learning efficiency of these approaches. If you look at the blue line here, this is just trying to maximize the predicted probability of activity by QSAR model. The model learns to do this incredibly quickly with not many steps. But if you take a more difficult problem like trying to minimize the docking score in this case to get better docking scores, it takes a lot longer. So it's a more difficult function to optimize for. And that requires many more samples. So in published works, this has taken up to around 3,000 CPU hours. And this is obviously a practical limitation. So in previous work that we published, we shared a variation to some of the reinforcement learning algorithms called augmented tail climb. And this just made a few tweaks to the algorithm to make the optimization more efficient. So not only was it able to learn to minimize docking scores further, but it was also able to learn to minimize docking scores to a particular threshold much faster by requiring fewer learning iterations. And this was on average for several different thresholds on 4 different GPCR systems, about a 45-fold increase in sample efficiency over reInvent. So what this does is it actually drops the computational resource now to something more like 63 CPU hours, which is a lot more reasonable. Of course, this is just ballpark figures because it really depends on what software you use, what kind of ligand preparation protocols, etc. So in this work, we wanted to use this new algorithm and test it on optimizing A2A receptor docking scores to try and identify novel A2A ligands. So what we did was we took a chemical language model, similar to the one I showed before, a gated recurrent unit, just a simple architecture that's been around for many, many years, and trained it on a curated subset from Campbell. Given this kind of pre-trained model, we then underwent rounds of augmented hill climb where we sampled molecules and scored them. Now here we predominantly wanted to minimize the docking score. So here we use Glide SP, along with also some extra docking constraints, which are quite important, as I'll show you later, as well as some other properties just to try and ensure drug likeness. So a synthesizability score using the RA score to try and ensure that we're not generating molecules that will never be able to be synthesized, as well as some simple phys-chem properties with a small typo here. So those were just simply log P, the number of consecutive rotatable bonds in your molecule, and the number of hydrogen bond donors it should have. And what we did was we optimized this kind of MPO score for just simply 12,800 de novo molecules per experiment. and this equated to around 12 hours over 20 CPUs. In other words, an overnight computation. So that's really the maximum you want to use if you're a computational chemist working on active projects. You can just run it at night and come back in the morning to see your results. And with this new sample efficiency and speed efficiency, it really facilitated us and enabled us to repeat this experiment on 7 different antagonistic systems and have a look at the differences. So it allowed us to answer questions like, how do the different systems, protein crystal structures that we use for docking, influence the type of chemistry we get back from the generative model? And what we did was we repeated this using 7 different X-ray crystal structures. So you can see the legend on the right with the different PDB codes. And you can see our different objectives here. So the top left is the overall MPO score that you see is optimized quite quickly over the 200 steps. And then you have the other parameters such as docking score, where in some cases it's minimized, in some cases it's already quite low and just remains slightly lower. And you can see for the properties during training, such as log P, number of rotatable bonds, and the number of hydrogen bond donors, it always stays within the limit that we set it. So it's able to stay within that property space that we really want in the ligands that we generate. So the first question we wanted to ask was, how do de novo molecules compare to known ligands? And A2A is a really nice case study to try and answer this question, because it's been extensively validated in the literature. And actually, there's a really nice previous paper called GPCR Bench, which proposes a set of chemotypes, known ligand chemotypes against the A2A receptor. So I have an example of what would be like a known ligand chemotype here, named 2C2. And it's really just a known substructure. This could be a scaffold, particular arrangement of functional groups active against the A2A receptor ligand. So first things first, you can see that each particular experiment, so each optimization against each different X-ray crystal structure, generally generates around 20 unique chemotypes that are already known to be A2A receptor ligands. And those are elaborated such that for each experiment, you can reach up to around 4,000 molecules per system, per experiment, where you're recovering that known chemotype. And actually, it's quite interesting because only 2 exact ligands were recovered per system. So you're really reaching into novel de novo chemical space. And I think this is kind of my favorite plot of the whole work. And it shows that the type of chemotypes that you recover really depends on what crystal structure you use, much like you would expect with virtual screening. But now we see it also with generative de novo design and optimization of docking scores. So you can see in some cases, for example, here, the AM-thiaz-12 chemotype was recovered 538 times, but predominantly by the 5-OLV PDB crystal structure. And in some cases where only a few examples of chemotypes were recovered, they're only recovered by certain systems. And this really kind of just demonstrates that, you know, changing the crystal structure used and the exact configuration of the binding pocket really has an effect in the type of ligand complementarity that you'll get by minimizing the docking scores with a generative algorithm. Another kind of question we had was actually, are we probing novel chemical space? And what I mean by novel here is practical novelty. So were any of the compounds that were generated present in what was being used as kind of like the purchasable library at the time? So this is a combination of Molport, Aldrich, and ChemSpace, and was about 12 million compounds. So we were checking how many of these de novo molecules existed in those libraries. And per run, which was, you know, approximately 13,000 molecules, 10,000 of them were valid, unique, and commercially novel. And around 3,000 of them actually already contained known A2A receptor ligand chemotypes. So we knew we were on roughly the right track. And you can see here this plot of kind of similarity to vendor compounds versus similarity to known A2A ligands, that you really have a range of novelty that you can access if you want to. If you want to search for a particular difference to vendor compounds or a particular difference to known A2A ligands. And we do recover some compounds in vendor libraries and some A2A ligands. Another question we asked was what difference it makes to have different constraints in your docking system. So we took some of the most qualitatively promising crystal structure systems, and we modified the different docking constraints that we used. So do we want to enforce that both hydrogen bonds to asparagine 253 are present? Do we want to occupy both lipophilic subpockets or just one lipophilic subpocket, etc.? So this really depends, and I suspect that it'll depend on the system you use as well. The default we used was the blue line here, and this was only one hydrogen bond requirement and only one lipophilic hotspot requirement. And what you find is you make it slightly more strict. For some reason, it dropped down to the yellow line, but you made it more strict again. So you want two hydrogen bond donors, a donor and acceptor, sorry, and you want occupation of both lipophilic hotspots, and then you recover more chemotypes again. But what's more difficult to measure here is that we saw a qualitative improvement in the kind of docking. So the poses we saw were more reasonable that we would expect for this particular system. So the next question was, how do you triage all of the molecules that we generated? So we pulled together all of the experiments, which resulted in around 180,000 molecules, and we just simply took the top 1,000 molecules by MPO score from each experiment. We clustered them based on chemotypes to help us triage them and go through them. We visually assessed the pseudo-APO water network with water mapping tools that we had. And then we eventually resulted in the selection of 42 topologically diverse compounds that we passed on to chemistry to kind of tell us, okay, what do you think is reasonable for you to make? What's synthetically tractable? And what resulted is 9 molecules that were successfully chosen and synthesized. So these are the molecules that were chosen and synthesized. And what's quite nice here is actually you have a relatively diverse range of topology that you see. In some other publications that kind of experimentally validate generative methods, you can see one chemotype that's just enumerated many times over with one different R group, for example. 4 of these compounds were novel. However, the other 4 of these compounds contained, that should be 5 of these compounds contain novel chemotypes. Sorry, the substructures highlighted in yellow are known chemotypes. And we actually found that 8 out of the 9 of them bound with a binding affinity less than 10 micromolar, so were considered hits, which is an incredibly high hit rate of 88%. And moreover than that, we went on to do functional assays to actually confirm that 4 of them were functionally active against the A2A receptor and also not active against the A2B receptor. So they were selective over A2B. But what we didn't necessarily expect was actually that although we found 2 inverse agonists and 1 neutral antagonist, which we were kind of expecting by choice of the docking systems we used, we also kind of serendipitously found 1 partial agonist.
1 more minute.
Okay, perfect. I'm almost done. And we took the 2 most potent compounds, and we also crystallized them with the A2A receptor. And you can see the crystal structures here with the predicted bioactive conformation by docking on the right. So although we were pretty much right on the bottom case, we were slightly off on the top case. And that kind of makes you wonder, when we achieve such a high hit rate, what else is out there? So if you cluster novel chemotypes with particularly low docking scores, of the 10,000 or so molecules, 70% of them already have A2A receptor ligand chemotypes, but also there is 3,000 molecules that could represent completely novel chemistries that are yet to be explored active against the A2A receptor. So in this work, we importantly validated generative workflow using different crystal structures and achieved a hit rate of 88%, which is the highest published hit rate compared to virtual screens against the A2A receptor. And what you really get is a considerable enrichment in the type of chemistry you get specific to the A2A ligands, while still achieving commercial novelty that you just cannot buy in vendor libraries. And although this work is kind of a mix of automated as well as human influence design in the triage of the molecules, so it's only level 1 automated design, it kind of raises questions as how do we actually move further down that list in terms of the levels of automated chemical design. How do we get to automated generation of molecules, but also automated selection of molecules? And with that, I'm done. So I'd like to just thank everyone from the Bender Lab from Cambridge, as well as everyone who took part in this experiment from Nextra Pharma, with whom it would not be possible. And I have a QR code link to the preprint if anybody would like to have a look, or I will hang around and answer any questions. Thanks very much.
Thank you very much. Yeah, fantastic talk. Do we have any questions here in the audience? Yeah, moment.
Hi, Morgan. That was a brilliant talk. Thank you. Most projects, you don't have the luxury of multiple crystal structures as your starting point. Can you give us any feel what would be the results if you had just, say, one?
I think you could still do a lot with one. And I think what's quite nice in the work we showed here was we also ended up with new crystal structures. So we actually closed the loop in our work where we could then iterate again, and with our new crystal structures, we could optimize for docking scores against those particular co-crystal structures. So one would hope that with one, you could find new potent ligands and kind of continue the loop. However, of course, it's incredibly system dependent. I think in this case, A2A was a very nice case study because we had some in-house expertise, but that's not always the case, right? So I do see a point. If you only have one, it might be less well validated. But I think if you can validate your system, then this is a very powerful workflow that you can employ for hit identification.
Any other question? Then let's go to the questions in the chat. So we have one from Fanjil Wang, who is asking, thanks, Morgan, for the talk. Could you comment on how reinforced learning works compared to other optimization algorithms, example, Gaussian optimization, etc.? Also, since it works on smiles notation, will it benefit from other representation, graph-based, for example?
Yeah, I think this is a really nice question. There are, of course, many, many different types of generative algorithms out there. Some of them are graph-based. So I'll start with that. There hasn't been any graph-based algorithm that seems to particularly outperform this kind of smiles notation. And it's important to remember that this smiles notation is a representation of the graph, right? So actually, unless you're doing work in 3D, smiles notation represents the graph anyway. So it's just the model that kind of learns that graph representation through smiles. In terms of comparison to other optimization algorithms, there's been work that have used kind of a hybrid reinforcement learning Bayesian optimization approach that also works very, very well for sample efficiency. So there's no reason you can't use both. I've never seen a pure Bayesian optimization for chemical language models, but I've seen it for other types of generative algorithms. And it kind of just raises a point to some of the other problems we have in the field, which is no unified benchmark that everyone agrees upon. But on the benchmarks that are out there, these models perform very, very well.
Okay, thank you very much. I think that in the interest of time, we're going to stop the questions now to give some time to the next speaker. So thank you very much for this fantastic talk. And then,
thanks very much.
Yeah, let's get ready for the next speaker. Our next speaker is Joe Greener. The talk is Reversible Molecular Simulation for Training Classical and Machine Learning Force Fields. So Joe did his PhD at Imperial College London with Mike Sternberg and a postdoc at University College London with David Jones. He has recently started a group at the MRC Laboratory of Molecular Biology in Cambridge working on improving molecular simulations. Currently, his work aims to improve the molecular mechanics force fields used to simulate biomolecules with machine learning techniques. He's also interested in developing new types of machine learning force fields that are fast enough to simulate biomolecules. So thank you very much for coming here, and the floor is yours.
Thanks very much for the kind introduction and for the invitation. So this work's kind of taken place over the last year or so. Hopefully should be out in a journal soon. The work is available at this preprint here if you want to have a read. So what I'm going to talk about today, I'm going to outline the various ways to take gradients through a molecular simulation. I'll talk about what that means and how they can be classified. I'm going to introduce a new technique called reversible simulation that overcomes the main drawbacks of differentiable simulation. This method is fast, is accurate, and it can be used to train both molecular mechanics and machine learning force fields to fit experimental data. And kind of one theme of this talk is that as we kind of go into the future, the next generation of force fields of all types are going to be trained using a variety of techniques. It won't just be mapped into QM data. Okay, so for this audience, probably don't need too much introduction here, but for those who aren't so familiar with molecular dynamics, you basically set up your physical system in a computer. So for instance, on the right here, you have a protein or a peptide in water with some ions. You define the rules that determine how things kind of interact, the forces, and then you basically press play, which in practice means doing numerical integration of Newton's second law of motion, F equals ma. It's very expensive. There's not really any shortcuts. And it's been successful over, more than 50 years now. It's helped us to understand many processes in chemistry and biology. Works particularly well when it's used kind of in an iterative process to either give mechanistic insight into experiments or to kind of suggest future experiments. And as we look to the future, we're going to kind of have more and more compute, all these amazing machine learning techniques, and kind of AlphaFold and better protein structure prediction means that molecular dynamics is going to be very important. So I mentioned the rules of how things interact. So that's called the force field. And in this talk, we're going to be talking about two types of force field. There's the kind of traditional molecular mechanics force field where you treat atoms as point charges, and you only consider kind of pairwise interactions. These are very fast. They can't do chemical reactions, but you can simulate large biomolecules with them. And they've been trained using a variety of techniques. You can match to high accuracy QM data, and you can also train to condense phase data. So that's things like density of water, enthalpy of vaporization, etc. And then recently, we've had this huge influx of machine learning potentials. So the appeal is very clear, right? If you use a neural network, it's a universal function approximator. They're slower than molecular mechanics, but they're considerably faster than density functional theory, probably, at least 3 orders of magnitude, even more. And to date, these are generally trained on quantum mechanical data only. So you need high accuracy, large data sets to do so. And so we want a kind of method that can train both of these types to match given experimental data in order to kind of enhance the QM data for training. It should be accurate, it should be generally applicable, and it should scale with parameter number nicely. So the best way to improve the parameters of your force field is to obtain gradients through a simulation. So what I mean by that is you run your simulation, you measure some property, say of the structure. It could be something like RMSD to a crystal structure, and then you calculate the gradients of that property with respect to all the parameters in the system. So all the force field parameters. And there's a number of ways to do this, and they roughly break down into the numerical approaches, the ensemble-based approaches, and the trajectory-based approaches. So I'll briefly outline those. So traditionally, you'd use a numerical approach. You would tune your force field manually, at least in part. So for instance, this study on the right here, basically, they tuned a few key parameters between the solvent and protein to make a biomolecular force field that is more applicable to disorder proteins. The advantage is that you can just use super fast software, GROMACS and the like, which can't do gradients because you just use it as a black box. But this scales poorly with parameter number. You can use kind of sampling approaches, but it still scales very poorly. And if you want to train a neural network with 100,000 parameters, this is clearly not going to work. the ensemble reweighting approach, it's really elegant, based on kind of Boltzmann statistics. So you have some observable L, and then the expected value on the right there in angle brackets is the value of L at each state multiplied by the probability of being in that state. And you can differentiate that. So you're basically differentiating the kind of the Boltzmann equation to get this general expression for calculating the gradient. And you kind of assume that the microstates sampled here come from your simulation. So see, for example, the force balance approach is very popular. Originally, the derivatives were found using kind of finite differencing, but this can be done with automatic differentiation, which I'll explain in a bit. Recently, this method has been made even more powerful via differentiable trajectory reweighting from this paper here, which uses thermodynamic perturbation theory and allows you to reuse the states to avoid recomputation. However, this and the previous approach ensemble reweighting suffer from one important drawback, which is that they cannot be used for loss functions that take in multiple states. Okay, so what I mean by that is if you have a diffusion coefficient, you want to measure position at time t0 and then at time t1 and see how much something's moved. That property takes in two states. So one way around this is to use trajectory-based approaches. So the first is the adjoint method. The math is a little, the notation's a little different here, but you can find out more about it in this 2018 Neuritz paper, neural ordinary differential equations. You basically differentiate the differential equation of the simulation before you actually discretize it and try and solve it. So you end up considering this quantity called the adjoint in its dynamics, and this is another very elegant approach actually, but it does have a drawback, which is that you get this kind of new adjoint equation, but it's unclear how to actually solve that. Okay, especially in the case of second order ODEs. So I mentioned the concept of automatic differentiation, so I'll describe that now. So if you imagine you have a series of mathematical functions on the top right here, so f, g, and h, and they're changing some input x into some output y. You probably remember from calculus that you can use the chain rule to get dy dx. And it turns out that this actually applies just as well to computer programs. Okay, so each line of your computer program can be thought of as one of these functions. And either it's differentiable in itself, if it's like addition or sine or something, you know the derivative, or it can be broken up into things that are differentiable. And so if you write your program in an AD framework like TensorFlow, PyTorch, JAX, whatever, then you can get the gradients of some output with respect to all the parameters. This is how neural networks are trained. It's basically the only thing used to train neural networks because the compute time is independent of the parameter number when you use reverse mode AD. So this can be applied to molecular simulation, where it's called differentiable molecular simulation. So let's think about what you're actually doing algorithmically in a simulation. So you're solving this second order ODE defined here. And one way to do that is the leapfrog Verlet integrator. So you have a forward step where you, for instance, calculate the forces using the force field. You get the accelerations from Newton's second law of motion. You update the velocities, and then you update the positions. And this is actually reversible. Okay, so you can step backwards as well, which will become important later. Now, in practice, you actually want to run in the, you want to keep temperature constant, so you run in the canonical MVT ensemble. And so you can use, for instance, Langevin dynamics, which adds a friction term and a Gaussian noise term, which represents kind of bumping with a kind of heat bath. And so the forward step is written on the right. It's just a little more complex than the Verlet step. But this crucially can also be reversed if you know all the noise terms. So can we do this AD technique through a simulation? Well, yes. You can use it directly on the integrator I just presented, and it gets you accurate gradients. You do need to be careful with gradients kind of exploding and vanishing, but there are ways to deal with that. The main drawback is that the memory cost of the simulation is basically linear in the number of steps, which is a pretty severe problem for molecular simulation where you want to do millions of steps. You can use checkpointing, and in some previous work I looked at this with regards to training an implicit solvent model force field. But now in this approach, we're asking, okay, we can use AD to take derivatives through all sorts of complicated algorithms, but a molecular dynamics simulation actually just repeats the same thing again and again. It doesn't have any branching, and it can also be reversed. So can we actually strip out the automatic differentiation, and can we actually just derive the gradients by hand? There are some technicalities about doing this in the MVT ensemble. You do need to run a forward simulation first, because you can't just run backwards in the MVT ensemble. So just a bit more on the maths. It turns out that if you want to get your gradient there, then it equates to this equation. This partial derivative at the start can be calculated at the end of the trajectory, and this partial derivative from the force field can be calculated each step. So the complexity arises in accumulating this middle term, the LDFI. And this whole expression kind of averages quite nicely for taking snapshots. So how do we calculate that accumulating term? Well, with the help of symbolic derivation tools, you can basically derive it for a specific integrator. So for instance, for the Langevin integrator I showed earlier, this is the first term. The second term is more complex, and the complexity just increases quite heavily. But the key point to take away is that each term can be constructed from the last. And so you can step backwards through a simulation and accumulate the gradients without storing many intermediate values. One nice thing about deriving this is that you do see how the gradients start to explode as you go backwards, which is what we found kind of in practice. And just kind of the last slide on the more in-depth maths. To do this, you basically need 4 accumulation values, and every step you have to calculate 2 gradient calls. So these can be done. These are vector Jacobian products for those familiar with AD. They can be done efficiently via automatic differentiation, or in the case of molecular mechanics force fields, they can actually be coded explicitly. And in that case, you're not using any automatic differentiation at all. There is the slight complication for machine learning potentials that you do need not just the forces, but the derivative of the forces with respect to coordinates. But that's usually achievable with using higher order AD. So how do we do this in software? We use this Molly.jl software, which I've been working on for a number of years now, which is an implementation of MD in Julia. So the Julia programming language is very nice. It's very fast, high-level language, which lets us write software with one language all the way down, which is not the case for most MD software. So it's closest in design to OpenMM in terms of its API. OpenMM, for those familiar with it, has a Python API, but under the hood it has all sorts of compute kernels. And so the principle here is that any kind of user-defined potential or simulator should be easy to define and just as fast as kind of the built-in features. There shouldn't be anything special about the built-in features. And so we can simulate proteins with the trajectories matching existing software, and it's differentiable using Zygot and Enzyme, which are 2 AD tools in the Julia ecosystem, somewhat similar to JAX. So just to give a quick outline of what this looks like in terms of code, you can load in a force field from XML files, for instance. You can then set up a system and properties to log. We then have an energy minimizer. We run the energy minimizer, assign random velocities, and then simulate using a Langevin dynamics with a Monte Carlo barostat to control the pressure as well. So that gets you something like the simulation on the right. So let's apply this reversible simulation technique to some examples. Water is a classic example for force field parameterization. So can we improve the Leonard-Jones parameters, sigma and epsilon, and the oxygen partial charge? And in this case, we use 2 loss functions, matched to the experimental radial distribution function and the enthalpy of vaporization. So the first check is that the gradients match reverse mode AD, which is mathematically the same thing, and indeed they do. On the right here, this is the kind of fractional difference between reversible simulation and reverse mode AD, and the error is basically numerical error, just due to different orders of floating point operations. And in practice, we do truncate gradients after 200 steps, and I can talk more about that later if people are interested. So the first surprise here was that we compared the gradients between our trajectory-based reversible simulation approach and the ensemble reweighting approach, and we were really surprised to find that the correlation is really very good across all ranges of parameters, but particularly kind of across the range of kind of more sensible parameters. Very strong correlation, and these are two different approaches, so that's interesting. There is some evidence that the reversible simulation approach is more stable over repeats. What I mean by that is that if you repeat the same simulations with different stochasticity in the thermostat, you'll get different gradients, but the variance of those gradients is lower in the reversible simulation case. So possibly you can think about that being a better gradient. So if we optimize those parameters I mentioned, the Leonard-Jones and partial charge parameters, in order to minimize the loss, we see that the optimization pathways on the right here are fairly similar for the reversible and the reweighting case. A bit smoother maybe in the reversible case, it's kind of less jagged. And performance in our software in this case is actually fairly good. On CPU, it's about 2.7 milliseconds per step compared to 2.3 if you're just doing a forward simulation. So you're really not adding much overhead. And by comparison, OpenM's about 2 to 3 times as fast. It's 1.2 milliseconds. We haven't looked at speeding this up on GPU yet, but we may do in future. So do those two properties, the entropy of vaporization and the radial distribution function, match experiment better after training? They do. This figure, I'm reworking this figure a little bit because it's not super clear, but the starting parameter are the TIP3P parameters in blue, so they don't match super well, which is why we trained from them. And our case is orange line here, so kind of under the red and purple lines, so it matches much better. And in the radial distribution case, again, TIP3P is, you don't see the correct peaks for the second and third peaks. And in our case, you have much better match. You'll also notice there's lots more lines here. So there's nothing special about the Leonard-Jones in this system, it's just a formula, so we can actually try other functional forms, right? Some of you may be aware that the repulsion term in Leonard-Jones is not particularly physically motivated, and so you can replace that, for instance, with an exponential term in the Buckingham potential, or you can introduce even more parameters with a double exponential potential, and all of these we can fit quite nicely. I notice on the board over here, for those in the room, someone's actually drawn up the Buckingham potential, so it's clearly very topical. Okay, so can we train on a system where we actually use a dynamic property that I mentioned you can't do with ensemble reweighting? So how about diffusion of the oxygen gas in water? So we replace 10 of the water molecules in our system with oxygen, and then you run a simulation, you measure the diffusion coefficient, and the loss is how well that diffusion coefficient matches the experimental diffusion coefficient, which it doesn't at the start with our starting parameters. But we can change the Leonard-Jones function. We can train the Leonard-Jones function to match much better. You can see that in orange here, we start at about 3.5 meters squared per second. And at the end of training, we're matching the experimental value of 2. And similar with the other functional forms as well. Okay, so I mentioned we don't just want to train molecular mechanics force fields, we also want to train machine learning potentials. So from the differentiable trajectory reweighting paper, they have a diamond system, where they train a DimeNet++ model with a Stillinger Weaver prior, and so we train a similar model using reversible simulation. So we match the stress and stiffness tensors to the experimental values. On the right here is shown the key values from the stiffness tensor, and over the course of training they match the experimental values well, with longer simulations shown as a cross at the end. And this model has 120,000 parameters, which is an indication that we can start to train machine learning potentials kind of using this approach. So to sum up all the kind of different methods available here, you have the numerical approaches, which are, I mean, they work. We've been very successful, but they're slow and they don't scale well with number of parameters. You have the ensemble ensemble-based approaches. Very elegant, they've worked well as well, but they're not applicable to the loss taking in multiple states. And then you have the trajectory-based approaches, which are maybe a bit newer, which are, again, elegant in their own way, but in the case of the adjoint method, it's unclear how to discretize the equation. And in the case of reverse mode AD, you have a high memory cost. So in this talk, this reversible simulation approach, although it's a bit untested and you kind of need to implement the algorithm, hopefully it's a new and useful method. And just to kind of motivate why we might want to create a method that can train to all sorts of experimental data, well, there's so much available there to train on. You have things like radius of duration for disordered proteins, whether two proteins interact, the flexibility based on kind of NMR or B factor data from crystals, protein ligand binding. You could even train on free energy data, phase changes, kind of whether you have protein aggregation, or the fit to experimental data, for instance, cryo electron microscopy density maps. So all of these things in principle can be used to train the next generation of force fields. So I'd like to thank the Stuart Shears group at LMB, who've been very helpful, contributors to the software, existing software like OpenMM and GROMACS that's been very influential, the scientific computing at the LMB, and discussions with various people in the community, particularly the open force field community, which has been very useful. We do have, as I said, I am starting my group, so we have a postdoc position available, and do come chat to me, and potentially PhD positions as well. And finally, thanks a lot for your attention.
Thank you very much. So let's see, we have some questions from the audience. Do we have any questions here in the room? Let's go to the... Oh, sorry.
Thanks for a nice talk. In your the previous slide, you showed a number of different loss functions. I guess the ideal force field would reproduce all of these, but is it the case that you're working on a certain problem, and so you would just want at least one of them to work?
Yeah, I mean, this is a kind of the fundamental challenge of machine learning, is that ideally you would have such a descriptive high accuracy quantum mechanics data set that you could just train the force field on that, and then all of these would just magically pop out. But in reality, I think you do need, I think some kind of top-down direction is useful to get a kind of, to get a more general force field, or at least general within the parameters of what you want it to work on. It is a challenge. I mean, nowadays, probably the last 5 years, we've seen much larger QM data sets arise, and so maybe one day there'll be this extremely expansive QM data set. But then the argument is, if you can generate that extremely expansive QM data set, you need faster methods anyway. You know, can't you just use that in the first place? So.
Any other questions? I think we don't have any more. So again, in the interest of time, let's move to the next speaker, as we were also delayed. So thank you very much for your talk.
All right, let me try to share my screen.
Our last speaker is Austin Tripp. Austin recently completed his PhD in the Cambridge Machine Learning Group within the Department of Engineering. Since 2024, he has been a research scientist at Valence Labs, research unit in the company Recursion. His research interests are on machine learning for scientific discovery, focusing on decision-making algorithms like Bayesian optimization. In the long term, his goal is to improve the performance and reliability of autonomous labs. So thank you very much. The floor is yours.
All right, thank you very much. Can I just double check if everyone can hear me okay?
Yeah, we can hear. Thank you.
Okay, perfect. And you can see the slide. Yeah, thanks so much for having me here today. Really sorry I couldn't be there in person. I had a stack of meetings on my calendar beforehand that prevented me from making the trip up to Cambridge. But nonetheless, I'm really excited to talk to you today. I'm going to give you a whirlwind tour of Gaussian processes. This talk's going to be a little bit different than the previous two talks you heard, where they were presenting their original cool science, whereas I'm presenting something that I've worked on and I've done variants of this, but I just think it's a general idea that's really like undervalued and not as well known as it should be within the chemistry community. So the goal of this talk today really is just to kind of get familiar and to maybe convince some of you to use Gaussian processes. I'm going to revisit this at the end, but let me set out a very specific goal here. I think if you're in the audience and you're someone who is regularly like trying to find the best ML model for your data set and you're using graph neural networks or random forests or other kinds of methods, I think you should try adding Gaussian processes to this list of models that you try. It might not be the best. It might not be suitable for your problem. That's totally fine. But I think there's enough tooling out there that means it's easy enough to try. And there's enough past works that show good performance that there's a reasonable chance that it actually could work very well. So I'm hoping that by the end of this talk, I can convince at least one of you to actually put this into action and try this. So let's move into the substance. I've put my talk into three sections, sort of the what, the why, and the how. Let's start with the what. What are Gaussian processes or GPs? Well, the very short answer is that they're a machine learning method. They're specifically tailored for regression. They're like a Bayesian method, and they give you uncertainty estimates, and they use like a kernel. These are like the most common terms that you might hear when you say what a Gaussian process is. And maybe you'll see images if you search on Google, like the one on the right here, some kind of interpolating between the data points. It looks kind of smooth. It has these nice error bars. Looks kind of cool. But I think beyond that, it's actually quite difficult to understand sort of what Gaussian processes are doing and why you might want to use them. And there's a lot of ways to derive a Gaussian processes. To derive Gaussian processes. A lot of them are very mathematically heavy. What I thought I would try to present today is like a very intuitive case, like what Gaussian processes are doing and why it kind of makes sense. I think the easiest way to understand this is actually forget about GPs for a second and focus on a much simpler method that many of you have probably used. This is k-nearest neighbors, or KNN. Well, if I was in the room, I'd ask for a show of hands. How many people have used them? But maybe just, I don't think I can see you guys. So just mentally, I'm hoping 50% of you have actually tried this on something like scikit-learn. But I'm going to give you a little refresher if you haven't. Imagine you have a training set of molecules, mol1 to mol(n), and you want to make a prediction for some unknown test molecule. The way KNN does this is it first computes a distance between every single training molecule and your test molecule, which I've just denoted as like D1 to D between 1 and star or something like that. Then you look at all these distances, find the smallest k distances, and that gives you sort of k indices. Oh, there's a typo on the side. That should be I1 to ik. It gives you a set of k molecules, which are the nearest neighbors, and then you make some kind of prediction based on these neighbors. The exact way you get this prediction can vary. If it's regression, you might just take the mean. If it's classification, maybe you return the majority class. But it's some variant of like look at the nearest neighbors and use them to make the prediction. So GPs don't depart from this, but not too much. The main difference is that instead of a distance function, we're going to use a kernel function. A distance function has the interpretation that lower values are more similar. So the smallest distance is 0. That's the most similar you can be. Whereas a kernel is the opposite. Higher values tend to be more similar. There's quite a few different kernels to choose from. That could kind of be a whole other talk, but like just two common ones that you might use if you open up scikit-learn or something like that would be this RBF kernel. It's something like e to the negative squared Euclidean distance between its inputs. Or maybe if you work with molecules a lot and fingerprints, you might use something like this Tanimoto similarity, which is like a sort of fraction of bits that overlap in the fingerprint divided by the total number of bits. But there's lots to choose from here, but these are broadly functions that are going to be higher the more similar the input is. So with that in mind, GPs are going to do something that's very similar to KNN, but just maybe a little more complex. Again, we start off with our training molecules and our query molecule. Again, we're going to form some kind of vector of sort of this kernel value between your test molecule and all the different training molecules. And I've drawn it just transposed here. But now here's where we're going to depart. We then form this additional matrix of the kernel value between every training point and every other training point, and then invert this matrix. And then we line up a vector of our labels for the training set. And then the prediction that the Gaussian process gives you is just the matrix product of all of these things, which ends up, if you look at the shapes and think about it a bit, it just ends up just being a one scalar number. So if you stare at this for long enough, you can kind of see that it's going to end up being a linear combination of the training molecules labels, and this combination, like the sort of the weight of molecules one, the weight of molecule one's label is going to be higher if the kernel value, the similarity between the test molecule and molecule one is higher, which is maybe intuitively kind of how you would expect these methods to behave, similar to nearest neighbors. I'm going to rewrite this in a slightly simpler form. This is how you might see it written in a textbook, something like that. This like k between x star x, k x inverse y, and maybe that will make it a little more clear that this is like just some linear algebra and a kind of weighted combination of the training data. But what sort of is really interesting about GPs is that along with this prediction, you also get a variance prediction that comes quite naturally. The formula looks a little bit more complicated, but if you break it down, it's basically two terms. One is you have some intrinsic variance of the test point, which is just given by the kernel itself. And then you have like a correction term, which is always positive. It's going to reduce the variance, and it's going to reduce it more as this test point is more similar to the different training points you've seen. And what's, I think, especially notable about this is that this variance estimate essentially comes for free, because if you look at this term, sort of the two expensive to compute things, this k between x star and x and k x inverse, these are things you've already used to actually make your prediction in the first place. So if you I guess do the linear algebra in a clever way, you've already done most of the computation for this, and then the variance estimate pops out without too much more effort. So that concludes my kind of explanation of mechanistically what GPs are. Again, summarizing, I would say it's kind of like k nearest neighbors, but like using just all the neighbors to different degrees rather than just like picking out the closest k of them. I'm now going to move on to why, although I'm very happy to come back and take questions on the what at the very end of this. So yeah, you might now ask this question: why would I want to use GPs for anything? Well, there's quite a few reasons, and also some potential things to be aware of, which I'll point out too. I think reason number one, important to any practitioner, is that they just seem to give pretty good predictions in a lot of practical problems. Not always, not always the best, but it seems like they perform pretty well in a lot of chemistry tests. I'm going to come back to this. That's going to be the next 3 slides, but I thought that really deserves to be number one. I guess number two is just the fact that they have this uncertainty estimate. I mean, as scientists, we all like uncertainty estimates. This is something that is a frequent clash between people in machine learning and people in science who want uncertainty estimates, and uncertainty estimates from neural networks are kind of notoriously unreliable. But so beyond just wanting that, this is really critical if you want to do something like active learning or Bayesian optimization, or even just some kind of out of distribution detection, defining your model's applicability domain. These are all really useful reasons why you might want uncertainty estimates, even if potentially you would have a slightly less accurate model, then maybe it's even worth it. And the final point is that because your GPs are relying on this kernel function that you can define by hand, you have a lot of opportunity to like insert your own domain knowledge. If you want some feature to be emphasized more or ignored, that's easy to do by fiddling with the kernel. I'm not going to get into how in this talk, but suffice it to say, if you Google around, there's lots of things you can find. Two negatives, which I just want to note here. GPs generally scale poorly to big data. You have to form this kernel matrix. You have to invert this matrix that has this like cost that's more than linear in the number of training points. So that is a bit of a barrier. It is, there have been a lot of research works to try to overcome this with approximations. I've worked on some of this myself, so it's not hopeless, but at least like if you want to just implement the formula from the previous slide, this is an issue you definitely run into with big data. And they also just don't work as well for classification because you have to do some approximations, and there's really not really good tooling for that. But that aside, on small data regression problems, I think these disadvantages don't really apply, and you're left with these 3 advantages in the left column, which I think are really worth paying attention to. So let me walk you through a couple of results just to sort of show you, give you a more empirical case of like what GPs are capable of. The first one, this is not my work at all, but it was actually presented at CCM, I think 1.5 years ago, something like that, by Ryan. This is the paper from a startup, Deep Mirror, which was basically trying to compare a lot of different machine learning methods and representations of molecules on a whole bunch of different tasks in drug discovery, which they divided into QSAR, so I guess like the kind of binding coefficients, that sort of thing, and like ADMET, so I don't know, solubility, that sort of thing. And And they generally found that, at least for QSAR, GPs, with variety of features were like clearly like the best performing method. For AdMet, it was like a little more mixed, but like they were still among the best methods. So I can let you go into the paper a little bit more for the details, but like this is, I think, like the clearest paper so far that has showed like GPs on average seem to work pretty well. And I guess one thing to note in particular is like random forest is one of the baselines here that they test. And I know that the people in chemistry really love random forest models. They seem to work pretty well. So if you have a, GPs or another model of that kind of type, which seems to work similarly to random forest in a lot of cases. So random forest users, I think that you should really try GPs. Next, this is something that I've worked on. I mentioned that there's difficulty scaling GPs to larger and larger data sets, but I think there's been a lot of research in this area and things are definitely improving. So together with some collaborators, we had created this data set called DocString. This is a data set of docking scores produced with Autodoc Vina. We made it for like, it's 250,000 molecules and 58 different targets. So it's quite a large data set. And I guess one of the nice things about this data set compared to other data sets you might find in the wild is that the labels are curated in a very consistent way. So it's all run with Autodoc Vina instead of aggregating, say, experiment results from 10 different labs that all use different facilities and have different annotation errors and whatnot. So it's kind of clean. So this table I'm showing you here is from this archive paper, which was another work I was involved in. I would say how you should read this is just note that this left part of the table is a variety of methods that are not GPs. And the right part is a variety of methods which are some kind of approximate GPs. Again, let's not worry about the details here, but some variant of GPs. I'm going to pick out two things from the table. First is that these approximate GPs are pretty uniformly better than XGBoost, which is like a tree-based method that similar to random forest that probably many of you use. So maybe a little bit surprising, but not maybe terribly surprising. They're kind of using similar features. The second is that depending on the approximation you use, the performance can like the prediction performance could actually be pretty similar to like some good graph neural networks out there. This is attentive FP, which is kind of a representative transformer-based graph neural network, which is a few years old now, but I guess was more state of the art when this work was originally done. And if you just look at the numbers, they're either matching or off by just a little bit. But the really important thing to note here is that this is just throwing away the uncertainty estimates that the GP gives you, whereas in just comparing based on this mean prediction. So it's getting these results, but also giving you an uncertainty estimate, which is, I think, clearly as scientists, we all would really care about, right? So because it's pretty new, I think that like it's not the generally perceived wisdom that GPs or methods are actually able to perform similarly to neural networks, but I think I want you to take away that this is changing. Final thing I'm going to show is something from my own work. This is where we did some Bayesian optimization and molecule design, a little bit in the same vein that Morgan was talking about in the first slide, but this is a much more toy task than what Morgan talked about. This is just optimizing some of these oracle functions, which are from a benchmark called Guacamole. They're all quite toyish, like similarity to some known molecule or something, or predictions from another machine learning model. So I wouldn't read like too much into this. But what I showed in this workshop paper was that if you use a pretty standard Bayesian optimization setup using a Gaussian process with the Nanomolar kernel on molecular fingerprints as the surrogate model in Bayesian optimization, this seems to do really quite well, and in particular is scoring higher than a lot of these RL methods, which are very popular, like reinvent. I would say don't read too much into this. Again, it's a toy task, and I think the authors of this original the authors who ran this original reinvent method didn't do like a really good job of tuning. So these numbers could change a bit, but I would say at the very least you can take away that like they are like comparable. It's not the case that RL is like way better or anything than like a more like probabilistic Bayesian optimization method. Those are all the results I had prepared. I could show you tables from other papers, but I thought at some point it would get a little bit repetitive. I want to now just move into the final section, which is how. So if suppose you're convinced, how would you actually go about using GPs? I have two things to show you here. First is GPs are actually in scikit-learn. This actually came as a surprise to me. I worked on them for 2 years before actually learning that they were they were included in the most popular machine learning package, but they are. Of course, this means that if you're a scikit-learn user, it's just like a couple of lines of code to try out Gaussian processes and modify your existing code. The cons of this implementation, having checked it out, is that they have a pretty limited selection of kernels. So if you want to do something like a Nanomolar fingerprint kernel, I think that's not in there. Although like maybe it's added now, it could be wrong. But you're a little more limited, and you don't have any automatic differentiation capabilities if you want to tune some of the Gaussian process parameters. But that aside, this is like a pretty well-tested and reliable out-of-the-box implementation that I would probably recommend as the go-to for a more applied audience. If you're a bit more serious and willing to invest more time, there is like a pretty good Gaussian process ecosystem within PyTorch, composed really of 3 packages: gPyTorch, which is like just a Gaussian process implementation built on top of PyTorch. Then there's BowTorch, which adds a lot of extra Bayesian optimization functions like acquisition functions or Pareto front approximations, like multi-objective stuff, like a lot of really good features in there. And then this final package, Gauche, which is a Python package that I contributed to, which has some extra Gaussian process kernels for molecules in chemistry specifically. So this is of course a lot more flexible. You can plug in features from your latest neural network model or whatever, or have some kind of GP neural network hybrid, which is also something I've worked on. So it completely integrates with PyTorch, and then of course you can optimize whatever you want with automatic differentiation. The main con being that it's not just 3 lines of code like scikit-learn. It's at least 10 lines of code to do kind of anything, and there's a little more that can go wrong. So it's a bit harder to use, and I wouldn't want to promise a great user experience if you're pretty new to this. But it's what I use, and I would say if you find scikit-learn's working well for you, I would recommend giving this a try. So that's most of the content that I have prepared. I want to now spend some time just kind of revisiting the goals of this talk and talking about maybe some other things I'm thinking about in this space. So if any of you have Googled GPs during this talk, you'll find that they're pretty old. They're from at least 2005. Sort of everything's there, and all like the fact that you could do various kernels on molecules. This is all there, and in some sources date GPs back to like the 1960s. So it's like a very established kind of model. So you might naturally think that if GPs are really so great, why haven't I heard of them? Why aren't they more popular? And that's a very fair question. I have 3 main answers to soothe any concerns. The first is like until at least, I don't know, 2000, they were basically just used in like geology and like geospatial fields, and maybe some time series stuff, because that was the context when they were kind of originally invented, and you have like pretty low dimensional problems that you can plot everything visually. So people really liked that, and it's kind of only more recently that people have realized that, oh, you can actually just use this in any field. I think also there's like a general lack of awareness of GP methods among chemists and cheminformaticians. This is changing, but it's if you pick a random cheminformatician and ask them, I think it's like, I would guess less than a third have really ever heard of GPs in any meaningful way. And I think until really quite recently, like maybe just 5 years ago, there were pretty few Python packages that would work out of the box and allow you to use GPs if you weren't an expert in them. And obviously that just makes it really hard to actually get them used in practice. But now I think these things are all fixed. There's more awareness. There's more precedence of them being useful in chemistry, and there's better packages. And I think now it's like the perfect time if you're working in cheminformatics to give them a try. So let's now finally end by revisiting the first slide here, where I said I want you to try use Gaussian processes. I think in this, I know this talk was a bit of a whirlwind, hence the title, but I wanted to just, if you remember 2 things, it's like there's evidence now that they can work pretty well. They make predictions. They give you uncertainty estimates. There's a reasonable chance that they'll work well for your whatever cheminformatics problems you're facing. And at least as of now, they're reasonably easy to use. You have out of the box with scikit-learn, a slightly less out of the box implementation with PyTorch. It's pretty easy for you to go out and try. Although I'm going to caveat that this out of the box promises do not really hold for these approximate GPs. They're also in there, but they're a lot more finicky. But yeah, that could be a whole other talk. So I thought I will wrap up there. I mean, if you're interested in GPs, I'm happy to answer questions. Of course, happy for you to reach out to me. Happy to be contacted. I'm personally very interested in like actually using these to design molecules. In my current role at Valence and Recursion, I've only started pretty recently, so I don't have any cool results to show you yet. And of course, I guess I'd have to run by and make sure that I can share results publicly when I do have them. But I think that should be the case. So I hope I can speak to you guys again within a year or so, and then show you all the great things we've been able to do. But until then, just happy to answer questions, happy to be contacted. And if this sounds really cool to you, please reach out to me about potential roles at Valence and Recursion. They have a London office, and I think they're growing. Thanks so much.
Okay. Thank you very much. Do we have any questions here in the audience? Yeah.
Thanks. Nice talk, Austin. You've shown that GPs work well for prediction for the particular example you showed, but how well?
Hello?
Hello, can you hear me?
Yeah, it just cut out for a second. You said they work well for prediction, but and then.
Then how well do they work for uncertainty estimation? For example, if you removed the compounds which the prediction was most uncertain, do you see an improvement in the predictions?
If I remove the compounds where it was most uncertain, do I see improvement in the performance?
So you should see if the estimate is accurate, as you move from less certain to more certain. If you remove the ones that are less certain, the predictions should improve.
As in, I take things out of the training set, and then the performance of everything else improves.
Well, I guess just a general question. How
sure.
you feel uncertainty estimation?
Okay, so I would say maybe general answer is like it's reasonable, and I'm sorry for not showing plots on that here. I think it's hard to actually measure uncertainty quantification, and I think one of the difficulties in the field is that there's not a lot of empirical comparisons where they're also looking at the uncertainty, just because so many methods don't even include uncertainty estimates. They don't really evaluate it. So I think it's okay. It generally improves, like the uncertainty estimates are better if the predictions are better. So and that kind of depends on the tuning. Maybe with regard to the second part of your question, I think it's almost never the case that performance improves if you remove things from the training set, because GPs have this kind of nearest neighbor property where only like the most similar inputs actually influence the prediction. So if it's uncertain in a region, then generally it's going to be uncertain in everything in that region. So it's not really going to affect things in other regions. So maybe overall answer is yes. I think it does well, with some few caveats. Sorry if that was not a super direct answer. Are there more in-person questions?
We got more questions in the audience? Yeah.
Okay, I'm seeing some questions online if no one is has a more in-person question. Raphael says, I remember having to use feature selection to work with GPs. Other general recommendations for big data and lots of features. Good question. Yeah, I mean, with any machine learning method, you have to do feature selections. Big data, I guess it depends what you're working with. I've found ECFP fingerprints for molecule predictions are like surprisingly good, even though they're very simple. But I've also not really worked on a ton of real problems, so I don't know how representative that experience is. Yeah, maybe technically the features don't explicitly matter. It's just the kernel, because the kernel can ignore features. I feel like that's the best answer I can give. But if you post more clarification to the question, I could potentially add more. I'm tempted to move on to the next question, just seeing time. Morgan says 2 questions. Do you know how GPs behave on data sets with many activity cliffs? Good question. Depends on the kernel, I suppose, you use. I think that's like activity cliffs, I think, are one of the reasons why you might not want to use something like a Nanomolar kernel, because that is essentially this Nanomolar similarity is pretty insensitive to small changes in the molecule, and activity cliffs are essentially small changes that have a big impact. So that's probably just a scenario where you'd want to be more careful about the feature selection. And very fair that if you can't end up finding a good feature representation, that then GPs are not going to work very well. That's one of the cases when you might try and it doesn't work. And second part of the question, I'm assuming uncertainty value is some sort of calibration. Yeah, the calibration is essentially the same as you do to fit the mean prediction. So this is like setting the hyperparameters of the kernel. So yeah, you need to do that, and depending on the values you set, things can work well or less well or well. I didn't mention this, but one of the nice things about GPs is you have like this sort of metric called the marginal likelihood, which is like a pretty decent approximation of like how good the fit is, both the predictions and the uncertainty. So that's like I'd say reasonably trustworthy single objective to maximize to choose these parameters. Hope that answers the question. Agamemnon is saying, is the uncertainty provided by GPs a measure of epistemic uncertainty or allotropic uncertainty? Very good question. It's both. You get both like an uncertainty without the noise and an uncertainty with the noise. I didn't actually show the formulas I showed previously. They would change a little bit if you add noise to it. It's just like adding an extra sort of diagonal term to one of the matrices. But so what I showed was the noiseless version. But yeah, short answer is you get both. And now Morgan Thomas, it's another question. Second question.
Possible, we are already running out of time.
I'm sorry. Okay.
No, go. Try to do it in 1 minute if possible, and then we can.
Okay. Second question. Uncertainty correlate with test instance accuracy. I would guess in general, yes, but not always. Like I think you can set the parameters in a way where the test accuracy could be good and uncertainty would be very bad. But I would say in typical usage, they seem to correlate in my experience, but I'm not aware of a good empirical study on this for chemistry specifically.
Okay, thank you very much. I think we need to give a big round of applause to all the speakers today.